folks, welcome to another set of Chemistry 1 video notes. In our second lesson of Unit 3, we'll be learning about molecular structures. Specifically, we'll be covering standards C.3.3 and C.3.6. By the time we're done with this whole lesson, you'll be expected to be able to draw structural formulas for simple molecules and determine their molecular shape, and use structural formulas of hydrocarbons to illustrate carbon's ability to form single and multiple bonds within a molecule. So let's get started. Now, before we go too far, I need you to remember two things that we've already learned. The first is the octet rule. Every atom wants to acquire enough electrons to look like a noble gas. They do this by losing, gaining, or sharing electrons with other atoms. You also need to remember that the valence electrons, the ones in the highest principal energy level, are the only ones that participate in bonding. If you've forgotten how to find valence electrons, you can use this handy chart here to my left. Let's start off with the Lewis symbols. Lewis symbols are representations of atoms with their valence electrons shown around the atom's element symbol. These electrons are represented by dots. To draw the Lewis symbol for an element, first write down the element symbol. Second, you'll want to place the correct number of valence electrons around that symbol. We place them one at a time as single dots in the four regions around the symbol: the top, bottom, left, and right. If we have more than 4 electrons, we can start pairing them up by placing a second dot next to one of the dots we already drew. A noble gas will have a full octet. In other words, it'll have 8 electrons around it. As you can see on the top right here, elements in a group or family on the periodic table have very similar Lewis symbols. They have the same number of dots around them because they have the same number of valence electrons. The only difference is the symbol itself. To show how ionic bonds form using Lewis symbols, you write down the Lewis symbol for both your metal and your nonmetal. You'll then transfer electrons from your metal to your nonmetal, creating a cation and an anion. Each time you remove an electron from the metal, you add a positive charge, and each time you add an electron to the nonmetal, you add a negative charge. By the time you're done, your metal should have 0 electrons around it, and your nonmetal should have 8 electrons around it. If that's not the case, you need to add more atoms in order to balance out your electrons. So let's do a couple examples of this. All right, so to show the ion formation using Lewis symbols, we first have to write out Lewis symbols. So the first example we'll do is magnesium oxide, MgO. Mg has 2 valence electrons, so it looks like this. And O has 6 valence electrons, so it looks like this. Okay, so the next step is to move our electrons. Our metal, magnesium, is going to lose its electrons. They're going to come over here. When we do that, that gives this a plus charge and this a negative charge. So now we've just made Mg, which has no valence electrons around it, and then oxygen, which now has 8 valence electrons around it. Mg has a 2 plus charge, and oxygen has a 2 negative charge. So we've got 0 electrons on our metal, 8 electrons on our nonmetal, and we've got a 2 plus, 2 negative. That balances out to equal 0, so we're good to go there. Our next example will be calcium chloride. So we know we have calcium and we have chlorine. Calcium has also 2 valence electrons. Chlorine has 7. So 1, 2, 3, 4, 5, 6, 7. If we start transferring electrons, we'll take 1 from calcium and put over here, giving the calcium a plus and the chlorine a negative. But once we do that, we don't have any more spaces. We've got 2, 4, 6, 8 electrons here now. So how do we fix that? We need to add another chlorine. So now we can take another 1 from calcium and move to this chlorine, making this a 2 plus and making this chlorine a negative. So basically you get a calcium with no electrons and a 2 plus charge, and 2 chlorines with 8 electrons around them, each with a negative charge. When we write that formula, we know it's CaCl2. Okay, let's talk about Lewis structures. They're similar to Lewis symbols, but with one addition: bonds. We use these to represent covalent molecules. In a covalent molecule, a bond is a shared pair of electrons, and we represent that with a single line between atoms. There are 3 types of bonds that we could have. Single bonds are shown as a single line, and they represent 2, or a pair, of electrons being shared. Double bonds are shown by drawing two parallel lines, and they represent four or two pairs of electrons being shared. I'll bet you can guess this next one, but I'll go ahead and say it. Triple bonds are three parallel lines, and they represent six or three pairs of electrons being shared. The octet rule works for most of the atoms we'll be working with in here, but there are a few exceptions. Hydrogen, helium, and lithium follow the duet rule, meaning they only want to have two valence electrons around them. Beryllium, boron, and aluminum are allowed to have incomplete octets, or less than 8 valence electrons. Other than that, the first 20 elements will follow the octet rule. Anything past calcium, the 20th element, is totally up for having an expanded octet, or having more than 8 valence electrons around it. You need to keep these exceptions in mind as we're creating Lewis structures. Now, I know, you're just dying to create some Lewis structures, but slow your roll. We'll get there. Let's talk about the steps to creating Lewis structures first. The very first step is to count up the atoms in your molecule based on the molecular formula you're given. Relate those atoms to their number of valence electrons, then find the total amount of valence electrons you have to work with. Next, you need to write down the symbol for your central atom. Of all the atoms you have to work with, pick the one with the lowest electronegativity value to be your central atom. Since hydrogen only wants one bond or two electrons attached to it, your central atom will never be hydrogen, even though it is sometimes the least electronegative. If you've got hydrogen, pick the next least electronegative atom to be your central atom. Next, go ahead and write the symbols for your other atoms around your central atom. Use the four regions that we used before, the top, bottom, left, and right. If you happen to have more than 4 atoms attached to your central atom, start squeezing the other ones in there somewhere. Once you have all your symbols written down, you need to start drawing single bonds, or just lines, between the central atom and the outer atoms. Once you finish that, you have what's called a skeletal structure of your molecule. You've got the basics, you've got things attached together, but we're not quite there yet. Each of those bonds you just drew represents 2 electrons being shared. So now you need to subtract 2 electrons from your total amount of electrons to work with for every bond that you just drew. This is going to tell us how many electrons we have remaining and still have to place on our structure. Now you can go ahead and place these remaining electrons around the outer atoms first, not hydrogen, remember, because it only wants 2 and it's already bonded. Place them as you do with Lewis symbols, one at a time, and then pair them up. Once you've placed all of your remaining electrons, check to see if you've got a full octet around each of your atoms. If you do, great, you're done. If you don't, convert some of your lone pairs of electrons into a bond. This is where we start getting into double or triple bonds. When you're finished, make sure all of the atoms follow the octet rule, if they're not one of the ones that we already talked about being an exception to the octet rule. Well, now here you thought this was easy, but sorry to burst your bubble, there's a few more exceptions and extra rules. If your total number of valence electrons is an odd number, you're not going to have 8 electrons around each atom. It's impossible, but that's okay. If you have extra electrons after placing them on the outer atoms, you need to start placing them on the central atom. And lastly, if you have a polyatomic ion, you have to account for its charge when you're finding the total number of valence electrons. So for every negative charge your polyatomic ion has, add 1 electron to your total. For every positive charge your polyatomic ion has, subtract 1 electron from your total. So let's do a few examples of Lewis structures. All right, I've got 4 examples here to do. We'll start off with carbon tetrachloride. Figure out how many total valence electrons you have. So carbon has 4, chlorine has 7, but you've got 4 chlorines. So 4 plus 28 is 32 valence electrons. Then we write down our central atom. Chlorine is way more electronegative than carbon is. So we're going to write carbon in the middle as the central atom. And we'll put the chlorine on the sides, like so. Next, we draw the bonds between the central and outer atoms. Remember, each of those bonds is 2 electrons. So we take how many bonds we just used, 1, 2, 3, 4, times 2. So we have 8 electrons we just used. 32 then minus 8 is 24. That tells us we have 24 more electrons to put around our atoms. So we'll start on the outer atoms. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 6, 12, 18, 19, 20, 21, 22, 23, 24. Now we've used our 24 electrons. So we're done with that. And then we go back and double check. Does each of our atoms have a full octet? So carbon has 2, 4, 6, 8 electrons around it, so it's good. Chlorine, 2, 4, 6, 8. And the rest of the chlorines are all the same. So all of them have 8 electrons around them. They're good to go. This is the Lewis structure for carbon tetrachloride. Next, we'll do selenium tetrafluoride. Selenium has 6 electrons. Fluorine has 7, so there's 28 plus 6 is 34 valence electrons. Do the same thing you did last time. Selenium is way less electronegative than fluorine is because fluorine is the most electronegative element. So we'll put selenium here, and then the 4 fluorines around it. Whoop, getting ahead of myself there. Okay, and then you'll draw your bonds. That's what I was already starting to do. Okay, now subtract your 2, 4, 6, 8 electrons you just used from your total, which gives you 26. Now you come around here and place your remaining 26. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, 12, 18, 24. We got 2 more. And we're all out of space on the fluorines because we already have 2, 4, 6, 8 on all of the fluorines. So selenium, being one of the ones that are past element 20, can have an expanded octet, which means we can put a lone pair of electrons there on the selenium atom itself. Now we go back through and double check. We already said all these fluorines have 2, 4, 6, 8 electrons around them. Selenium's got 2, 4, 6, 8, 10, and it has an expanded octet, and that's okay because it's past element 20 on the periodic table. Next we have SO2. S and oxygen both have 6 electrons, so now we have 6, 12, 18. Sulfur is less electronegative than oxygen is, so we're going to put sulfur as our central atom. We'll put our oxygens out on the outside there. And then we'll start putting our bonds, so boom and boom. So now we just use 2, 4 electrons, so minus 4. That gets us 14. We have 14 more to place. So we're going to put them on the oxygens because they're the outer atoms. We'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We still have 2 more, so we got to place on the sulfur, 13, 14. Okay, now we check to see if they all have 8 electrons around them. We have oxygen with 2, 4, 6, 8. Oxygen with 2, 4, 6, 8. But sulfur has 2, 4, 6. And it's not hydrogen, lithium, or helium, so it can't have... And it's not hydrogen, lithium, helium, beryllium, boron, or aluminum, so it can't have less than 8. It can't have an incomplete octet. So we need to move some of our electrons into a double bond. We can't move these electrons over because that would give 2 more to the oxygen that already has 8. So we've got to move any one of these 6 pairs of electrons around the oxygens. So we'll just take that and move it down here. And all we do is erase these guys and turn it into a double bond. So now you have 2, 4, 6, 8 electrons around oxygen, 2, 4, 6, 8 electrons around sulfur, and 2, 4, 6, 8 electrons around that oxygen. And finally, we'll do a polyatomic ion for you. Ammonium is a +1 charge. So we count up the electrons. Nitrogen has 5. Hydrogen has 1 each, so there's 5 plus 4 is 9. But it has a positive charge, which means it has 1 less electron than it should have. So -1 for the charge, and that gets us 8 valence electrons. Hydrogen can never be our central atom, so we've got to pick nitrogen, even though it is more electronegative than hydrogen is. So we'll put nitrogen in the middle. We'll put our hydrogens on the outside. We have 1, 2, 3, 4 of them. We'll draw our bonds in. We have 1, 2, 3, 4. And that gives us 2, 4, 6, 8 electrons we just used. So minus our 8 from our bonds gives us 0, and we're all done. That makes sense because we can't put any extra electrons on hydrogen anyway. And we also can do that for nitrogen because nitrogen doesn't want an expanded octet. The last step to polyatomic ions, and it's not a necessity, but I really prefer it if you do, is to put brackets around that with a +1 charge on the outside so you know for sure that that is an ion and not a molecule. Hydrocarbons are a truly interesting phenomenon that we'll practice drawing Lewis structures for. Fortunately for you, I'm not going to ask you to name these hydrocarbons until you get to Chem 2 next year. But just so you're aware, there are 3 types of these simplest hydrocarbons. There are alkanes, alkenes, and alkynes. Alkanes have single bonds, alkenes have at least 1 double bond, and alkynes have all kinds of fun with at least 1 triple bond. Single bonds allow for a fully saturated hydrocarbon, meaning it has the most amount of hydrogens that you could possibly have. Each time you change one of those single bonds to a double or triple bond, you reduce the number of hydrogens that could be attached to your carbons. The only thing I need you to know about this for this year is that when we draw the Lewis structure for a hydrocarbon based on its formula, it's important to draw it similar to how the formula is written. So let's do some examples of that. All right, again, for the hydrocarbons, I don't need you to go through all of the steps of writing the structure and valence electrons and all that. I just need you to basically write a decent looking structure and make sure that everything follows the octet rule. To do that, we just look at the way the formula is written. I'm going to give them to you like this so it's very easy. So for H3CCH3, it happens to be ethane, if you're curious. We have a C with 3 H's, and it's attached to another C with 3 H's. So that is an alkane, because it has all single bonds between the carbons. Okay, for the next one, you might notice there are 1, 2, 3 C's in there. It's probably easier than trying to read it and go through like we did on the previous one, just to go ahead and put your C's. Those are your central atoms, basically. So we're going to have 3 C's all attached together like this. And then look at where your H's are. So you have 3 H's here, 2 on this one, and 3 on the last one. This one is also an alkane, happens to be propane. Pro meaning there are 3 carbons, and the ane part meaning it's all single bonds. All right, if you've been following along closely, you might have seen I changed something over here. Don't worry about it. I made a mistake. It happens sometimes. So let's go ahead and draw this one. We have 1, 2, 3, 4 carbons, so we're going to go ahead and draw that. 1, 2, 3, 4. This carbon has 2 hydrogens attached to it. Notice I didn't go straight up and down or up and to the left or something like that, because with the Vesper theory, remember, these bonds want to be as separated as they can be. So this trigonal planar, I guess if you want to call it that, if you ignore the rest of all that, that would be the shape that would take. Then this next carbon has just 1 hydrogen. You could put it on either side. I don't care. We're not there yet. This carbon has no hydrogens, and this one just has 1 sticking out the side. Again, that's going to be the furthest away it can be from that other bond. Something different about this one. You might notice the previous 2, all of our carbons just had 1, 2, 3, 4 bonds around it. We didn't have to think too hard about the octet rule because it just automatically satisfied the octet rule. This guy, on the other hand, is a little bit different. So this carbon has 2, 4, 6 electrons around it. This one has 2, 4, 6. This one only has 4. And this one only has 4. So we need to be a little creative with the number of bonds that we put around our carbons in order to fix this. So we cannot add any bonds to the hydrogens. Hydrogens only want 2 electrons, so they're done. But we could add another bond right here, make it a double bond. That makes this 1, 2, 3, 4 bonds around that carbon, so it's good to go. This carbon now has 2, 4, 6, 8 electrons, so it's good to go. This carbon only has 2, 4. We can't add any here because that would change this number, so we're going to have to add it here. Now it has 2, 4, 6. Now it has 2, 4, 6, 8. So this carbon's good to go. It has 4 bonds around it. And then this carbon has 2, 4, 6, 8 electrons around it now, so we're good to go. This has a double and a triple bond. So it's kind of a little special. It's both an ene and an ine, an alkene and an alkyne. So again, for this year, all you need to know is how to go from here to here. I don't need you to write the names down. I don't need anything special about them. I just need you to be able to read this formula, draw it out like this, and put bonds where you need them to satisfy the octet rule. Okay, only 4 slides left. You can do it. Now that we know how to draw Lewis structures, we can use those to determine the shapes of our molecules. The shape of a molecule is largely based on the valence shell electron pair repulsion theory, or the Vesper theory. Basically, electrons are all negatively charged, and like charges repel each other, so electrons don't like each other. Those electron pairs, both the lone pairs and the bonding pairs around your central atom, are going to repel each other and fit into a shape that gets them the maximum distance away from each other as they could be. After you've created your lowest structure, you'll use the number of electron regions around the central atom in order to determine the electron geometry. The electron geometry tells us the shape the electrons are arranged in. This includes all electrons around the central atom. Based on how many of those electrons are bonding electrons or lone pairs, we can determine the shape of the atoms are arranged in, or the molecular geometry. Think of it this way. Imagine having two atoms attached to your central atom, but having no lone pairs of electrons around your central atom. Which shape here do you think is more pleasing to those bonding electrons? The one where they're the furthest apart from each other that they can be, or the one that has them a little bit closer together? Since those electrons repel each other, the correct shape of this molecule is the one on the right here. So how do we find the shape? We get our lowest structure taken care of, and then you need to count up the number of lone pairs of electrons that are on your central atom. Next, you need to count the number of bonding regions. You only count how many regions of bonds there are, not how many lines you drew. So single, double, and triple bonds, they all count each as one region. Add these two numbers up and it gives you your total number of electron regions. So the total number of regions that have electrons attached to that central atom. This number will determine the electron geometry of the molecule. Compare that number to the chart that you have. There may be multiple rows on the chart that have the same number of total electron regions. So you go to the next column in the chart and find the correct number of bonding regions based on what you just counted. This will give you your molecular geometry. So let's take the Lewis structures we already have and compare them to our chart to find their shapes. Okay, so you need your Lewis structures to find the shape of your molecules. Conveniently, I already have these here, so we'll just use these. The first step is to count up your non-bonding regions around the central atom. In other words, how many lone pairs of electrons are on your central atom. Carbon has no lone pairs of electrons, so it is 0 non-bonding regions. And then our bonding regions is how many places have bonds around the carbon. So 1, 2, 3, 4. There's 4 bonding regions. We add those up, we have 4 electron regions. And if we look at our chart, 4 electron regions means it is tetrahedral for the electron geometry. And since there are no lone pairs in 4 bonding regions, then it is also tetrahedral for the molecular geometry. For selenium tetrafluoride, we have 1 non-bonding region around the selenium. Then we have 1, 2, 3, 4 bonding regions for a total of 5 electron regions. If we look at our chart, electron region-wise, this is a trigonal bipyramidal shape for the electron geometry. And then if we just look at the 4 pairs and not the bonding one, it's going to be a weird seesaw shape. I'm probably not going to give you any shape-wise that's as difficult as those, but they're good to know. Okay, next we'll do sulfur dioxide. We have 1 non-bonding region. We have 1, 2 bonding regions for a total of 3 electron regions. That tells us we have a trigonal planar electron geometry, which means we have a bent molecular geometry because we have 1 non-bonding region. And last but not least, this one's just the same as this one up here. It's all going to be tetrahedral. Once you have the correct geometry, you can redraw your Lewis structures to reflect that geometry. This takes a lot of practice, and the best way to learn it is just by doing it. You'll need to look at your chart as you're first starting out with your practice. But as you get familiar with it, you should be able to do some of it on your own. To show the 3-dimensional shape of the molecule on a 2-dimensional paper, we have to distinguish between our bonds based on how they're oriented. We'll practice with some molecule building kits to build those molecules and physically see those shapes. But again, as you become familiar, it'll become second nature. Single lines are considered in plane with the paper. In other words, if we were looking at the 3D model, they'd both be the same distance away from you as you're looking at them. Bonds represented by solid wedges are coming out of the paper, or they're coming towards you, and bonds that are represented by dashed wedges are going into the paper, or they're going away from you. Let's take our previous Lewis structures and their shapes and draw them correctly now. All right, we've got the Lewis structures, we have the shapes, and now we need to draw those Lewis structures in their correct shapes. I promise it's not as hard as it looks. Just get used to it on the chart, and then you'll get the hang of it. So, tetrahedral shape for our molecular geometry. We're going to have a carbon here. We'll put 1 chlorine that just goes up, 1 chlorine that goes down and to the left a little bit, 1 chlorine that comes out of the page towards me, and 1 that goes away from the page, or away from me into the page, that's a capital C. That goes that way. That's what a tetrahedral shape would look like. For the seesaw shape, again, I'm probably not going to ask you to draw something this complicated, but you'd have selenium in the middle. There's a fluorine that comes up, a fluorine that comes down, a fluorine that comes out this way, and a fluorine that goes back that way. And our bent shape, this would just be like this. It's just bent. It was trigonoplanar with the electrons here, and then we took the electrons off, and that's the shape we have. And this tetrahedral will just be the same as up there. I guess if you want a couple extra seconds on your notes video, I'll draw that for you too. And there you have it. Well, that's it for today, folks. I hope this helps you to get started on your way to mastering these two standards. As always, let me know if you have any questions.